This is a practice exercise from page 178 in the textbook. We're dealing with a constant pressure, or what is sometimes called a coffee cup calorimeter. So a constant pressure calorimeter puts us in the unique situation where Q equals delta H. That is, the heat absorbed or released in the reaction tells us the enthalpy change of the reaction as well. So we're mixing two liquids. We have a reaction that's taking place, and you can see from the reaction that this is a precipitation reaction. And they're asking us what we have for the delta H of the reaction. We should note that they're specifically asking us for the enthalpy of the delta H in units of kilojoules per mole of silver nitrate. So that's going to help us understand exactly how to break down the solution. We should know how to get the kilojoules, so we should remember that equation Q equals mc delta T. So the heat absorbed or released is equal to mass times the specific heat times the change in temperature. And we do have all of those pieces of information. They're telling us the mass, they're telling us the specific heat, and they're telling us the change in temperature. But that's only half of the answer. That's going to give us kilojoules. We also need to get the moles part. In order to get the moles, we're going to go back to using molarity and volume. So there's actually two calculations we're going to need to do. And there's one more thing we need to talk about, and that's the setup of a calorimeter. So the way a calorimeter works is you've got your reaction that actually takes place in the middle, so RxN for reaction, and then outside of your reaction, you actually have your calorimeter. So what we have here is a situation of a system and surroundings. So that means if the temperature increases, that means that the reaction is releasing heat. So from the point of view of the reaction, Q is going to be negative. But from the point of view of the calorimeter, Q is going to be positive because the calorimeter is gaining heat. So what this ends up meaning is that the Q of the reaction is equal but opposite to the Q for the calorimeter. And again, that's because any heat released by the reaction is going to be gained by the calorimeter. So pay attention to your sign when you're solving these problems. So let's first start by figuring out what the Q of the calorimeter is. So we know that what is in the calorimeter is going to be the mass of the two liquids that we're mixing together. And they're telling us that the combined mass is 100 grams. They told us that the specific heat is 4.18 joules per gram degree C. And they're telling us that the change in temperature is ending with 23.11 degrees C, starting from 22.30 degrees C. Change in temperature is always final minus initial, TF minus TI. We should always double check to make sure our units are going to cancel out, and we should see that the grams will cancel, the degrees C will cancel, and we'll be left with units of joules, which is what we want. So if we go ahead and do this calculation, we'll figure out that the heat for the calorimeter is equal to 338.58 joules. And if I write that in kilojoules, that's 0.33858 kilojoules. I'll worry about rounding when I'm actually completely done. Now, since we know that the calorimeter got warmer, this answer is reasonable, that we'd have a positive heat value for the calorimeter because the calorimeter absorbed heat. It got warmer. Well, if the calorimeter got warmer, it must have absorbed that heat from somewhere, and it absorbed the heat from the chemical reaction. So the Q for the chemical reaction is going to have the opposite sign, but the exact same value, 0.33858 kilojoules. And again, this makes sense because the reaction must have released heat. That's why the solution got warmer. If it released heat, it's exothermic, which is why it has a negative sign. So that takes care of half of our answer. Remember that they want our answer in kilojoules per mole of silver nitrate. So the next thing we need to do is figure out how many moles of silver nitrate we have. And we can do the moles from the molarity, just like we were doing in the last chapter. That 50 milliliters, that's the same thing as 0.050 liters. They've told us that there are 0.100 moles of silver nitrate in every liter, which means we have 0.005 moles of silver nitrate. So now we have the two pieces. We know the kilojoules and we know the moles, so it's time to put them all together. Remembering that since we're at constant pressure, Q is going to be equal to enthalpy, so the enthalpy change for this reaction is going to be equal to negative 0.33858 kilojoules that were released when 0.005 moles of silver nitrate were reacted. Now we can go back and look at our significant figures, and we should see that the specific heat is going to limit us to 3 significant figures. So when we do this calculation, we're going to get a final answer of negative 67.7 kilojoules per mole of silver nitrate. We should always go back and check our answer, make sure that this seems reasonable. So the negative sign makes sense because we know that during this reaction, the temperature of the mixture increased. The only way the temperature could increase is if the reaction was releasing energy, if it was an exothermic reaction. Also something to think about. They're asking us this kilojoules per mole. We don't usually see delta H or enthalpy values in kilojoules per mole. We usually just see them written as kilojoules. And that goes back to how these chemical equations are set up. The way that this reaction is written, it's written for every 1 mole of silver nitrate that's reacting. So you could definitely see this as just this reaction and then a delta H of negative 67.7 kilojoules written at the end. They don't always tell you per mole of each substance because you can use the balanced chemical reaction to figure that out. So when you're solving these problems, just pay very careful attention to what they're specifically asking you for, and since they specifically asked us per mole of silver nitrate, those are the units we used for this problem.